Now that we've discussed the n-slit diffraction pattern, it'll be fairly easy to understand the application of n-slit diffraction pattern. In the most common use of that is in a diffraction grating. And so this is a periodic array of some kind of repetitive structure. So the structure, let's say, is lines on a transparent object, which can modulate either the amplitude or the phase of the wave that's going through this structure. And the first one is called a transmission grating because of that, because the wave just passes through some transparent object and then encounters this repetitive array of structures that alters the phase of the wave going through, and maybe if it is sufficiently dark or something, it can also alter slightly the amplitude. And as we've just seen, we'll get a principal maxima in various directions, and those principal maxima are labeled as 0, 1, or -1, depending, because there's a straight through beam that will be called the 0th order maxima. These gratings, diffraction gratings, were first invented in the late 1800s by Rittenhouse and also Fraunhofer. The reflection grating turned out to be more useful because it turns out to be easier to make them on these metallic, on a thin metallic layer on top of these structures, on top of a transparent slide. And in this case, the plane waves are coming in, and as you can see, we have inscribed a pattern on a high reflectivity metallic layer, and now we get reflection. And of course, you'll get the straight reflection or specular reflection of the at the same angle as the incident angle, and that's the 0th order beam. And then you get the first order beams on either side of that, which is again, these are the principal maxima coming from the diffraction pattern. So let's analyze the two situations, which will give us immediately the grating equation. So we've already seen how the irradiance from n slits or n sources looks like. The one difference here is that the incident beam can have an angle theta I that comes in to these n slits or n oscillators. So when the incident beam has an angle theta I, that means that there can be an extra phase difference or path length difference, which is given here by this CD. And so the two oscillators in this case will, the phase difference at any angle theta m, to say the mth order maximum. So of course, the normal phase difference between two of these is a sine theta m. But then we have to subtract the fact that that this oscillator is leading this oscillator by a sine theta I, and therefore the total path difference. So remember, this is going to lag over here and this one is going to lead over here, so they come in with opposite signs. So you get a sine theta m minus sine theta I. Similarly, in the reflection grating is the same argument. This incident beam is coming in at an angle theta I, and if I look at the mth order, sorry, that keeps doing that, the mth order is simply obtained by again, by the same argument, is going to have an extra path length difference, which is seen here. It's AB would be the path length difference normally if the beams were just being coming directly from the oscillators. There would be this extra path length difference AB. But now, because this guy has arrived at an angle theta I, then there is an extra path length of CD that occurs between these two beams, and therefore that extra path length, which is traveled by this light has to travel an extra path length CD to get to this second oscillator. So the total path difference is AB minus CD, which is this formula once again. So no matter which the transmitted or reflected grating, the path length difference is A times sine theta m minus sine theta I. Notice we are measuring the angle theta I with respect to the normal to the array of slits. Okay, this will become important later, but for now, this angle of incidence introduces a constant phase between the slits. So it's like a phased array radar. As if you remember back then, we had an extra path length, extra term epsilon, let's say, that we could introduce between two sources. And the principal maxima then are simply obtained by setting that overall path length difference again to m lambda. which gives us this formula over here. And that is our location of the principal maxima. The mth order beam or the mth order principal maxima is given by this formula over here. Now, one of the things that you would have noticed, and which is I think fairly obvious, is that there's always going to be the 0th order beam. Okay, there is a 0th order beam over here, which has m equal to 0 in the transmission grating and in the reflection grating. And then the reflection grating, that is just exactly bouncing off at an angle that when if you look at this formula here, if m equal to 0, which is a 0th order beam, that means sine theta m equals sine theta I, right? Which is exactly what you get for reflection when you are coming off of a reflection grating. So let's just look at the reflection grating here. So one of the problems that we were just discussing is that a lot of the intensity is in the reflected beam at the m equal to 0 order. So as we just saw, if m equal to 0, then in the earlier grating equation, which is on this slide, if m equal to 0, then sine theta m equals sine theta I, or theta m equals theta I, which is the reflected beam, right, from a reflection phase grating. And that reflected beam does not depend on wavelength because m equal to 0, so the right hand side of that equation does not depend on 0. Therefore, does not depend on wavelength. Therefore, the whole point of a diffraction grating is lost because we are not able to separate out wavelengths based on their angle. As a way to fix that, we use the same idea from phased array radar, where we change the phase between the individual oscillators in a certain manner, and the way to do this in the optical frequencies was by changing the shape of the grooves. So if you control the shape of the grooves, then this is analogous to changing the phase between the radio antennas, and that controls the angle which has the maximum direction. So a simple way to think about that is that we have, let's say we have a single slit, let's say a single slit let's say this is a reflective surface, and if a beam were to come in to this surface, normal to that surface, then of course the maximum intensity is reflected back right into that beam, and that is the highest intensity that is reflected back towards the incident beam. And if you want to consider diffraction around this, then this will follow the diffraction, the single slit diffraction pattern, right? You'll get the single slit diffraction pattern that we just talked about earlier, and you might get some intensity in these adjacent peaks, but it will be a lot weaker than in the principal maximum of this reflected facet. So the idea that R.W. Wood came up with is to tilt this surface a little bit, so that so if I call this width B, then when I tilt this, now if I come in with a beam that is at an angle to the normal, so this is the normal to our beam, then it's going to get reflected, and this is where the principal maximum from this beam is going to be, right? The principal maximum of the diffraction pattern from a single facet is now going to be at an angle relative to the incident beam. So we use that tactic or that idea to now increase the intensity. So the location of the peak in that single facet diffraction pattern is now controlled by the angle, this angle, the blaze angle as it is called, which is given by the tilt of an individual facet in this diffraction pattern. And as I said, it was first realized by R.W. Wood in 1910. So this was first, as I said, realized. So let's just analyze that situation. So now I'm bringing the beam in normally to the grating. So the beam comes in exactly normal to the grating. So the reflected beam would not, the 0th order beam or reflected beam would go back exactly along the same direction. That would be the 0th order. But now, because it's got this facet over here, the sum of that beam is going to get reflected at that angle. In fact, a lot of it is going to get reflected at that angle, right? Because if you think of this as a mirror, then this mirror has a normal which is at an angle to gamma with respect to this incident beam. So the reflected beam from one of these facets is going to be at an angle 2 gamma relative to the incident beam. So again, in the diffraction condition, if theta I equal to 0, theta 0 equals 0, which means that normally the reflected beam would go back along that direction. But for the specular reflection of this grating facet, we have theta I minus theta R. Again, in this notation, remember, theta I is the angle with respect to the grating normal, which is this angle over here, and theta R is again the angle with respect to the grating normal, which is that. For that specular reflection of the grating facet, theta I minus theta R equals 2 gamma. Since theta I equal to 0 in this case, the normal incidence, this is what I've done here. We are measuring with respect to the normal to the grating. The theta m, the angle relative to the to that grating normal, is going to be minus 2 gamma. The minus sign just is due to the fact that they are all on the same side of the normal. So if I were to slightly tilt this beam, it would be over here. That would slightly tilt this beam, but they'll both end up on the same side of the grating normal as in this example. And that's because I rotated in a positive or direction. Gamma, I'm assuming, is at an angle which is shaped that way if I from the horizontal. Okay, so in the counterclockwise direction. Sorry, that's what I was trying to say. So for the order m, to satisfy the grating condition, a sine theta m must be equal to m lambda. Remember, sine theta I will be 0. So in the grating equation, we can put theta I equal to 0. So we get a sine minus 2 gamma equals m lambda. So negative sign because that's the same side of the grating normal. So by changing this gamma, we can basically get a reflection. By changing the Blaise angle gamma, we get a diffraction angle theta m for the mth order beam at 2 gamma, okay, which will satisfy the condition a sine minus 2 gamma equals m lambda. So this allows us to, in fact, control the amount of, and that will give us the brightest beam that comes out from this blazed grating, and that will be the order that we can choose. If we satisfy a sine 2 gamma equals m lambda, that will give us the brightest beam in the mth order of the grating. And so this is a way in which we can control the intensity of the different orders of the grating. So now let's imagine a source that is perfectly narrow in frequency. After and so what we're doing is we're going to use the grating as a way to do spectroscopy on different sources and on their different lines that come out from sources, because the source, for example, some atom or some other white light source or any kind of source you may have, will not have exactly only one line that comes out or only one wavelength that comes out of it. It may have many different frequencies, and we can use the diffraction grating to analyze that. So imagine that now, though, that we have a perfect monochromatic source, which is infinitely narrow in frequency. Then, after passing through the grating, we know the width of the principal maxima is given by delta alpha equals 2 pi over n. And since alpha equals a cosine Ka over 2 times cosine theta, delta alpha will vary with delta theta just by differentiation. Sorry, it was K over 2 sine theta, I think. Yes. So this is K over 2 cosine theta delta theta, and we are setting that equal to 2 pi over n. And therefore, we arrive at what is called the instrumental broadened angular line width of a perfect narrow source. Even a perfectly narrow, a single line coming out from a source will have some small angular broadening when it comes out of the grating. That angular broadening is delta theta equals this formula over here, 2 lambda divided by Na times cosine theta m. So it varies inversely with the width. Remember, the width of the grating is going to be the number of lines n times the width times the spacing between the lines. So it varies inversely with the width of the grating. So if you want very small instrumental broadening or angular line width, you want to make the grating as wide as possible. So a bigger grating will give us better resolution of each individual line in this situation. We also have another important parameter. If I have two different sources now, or two different frequencies, lambda 1 and lambda 2, which are slightly separated, then the question is how far apart are they in angle? And that is just obtained by taking d, which is the angular dispersion, is defined as d theta over d lambda. So simply differentiate the grating equation, a sine theta equals m lambda, and you get that the dispersion, the angular dispersion, is just m divided by a cosine theta m. So this is the angular separation of closely spaced wavelengths, and as you can see, it varies inversely with the spacing between the grating lines. So a, 1 over a, right? So as a decreases, this angular separation or angular dispersion will increase. And so finer rulings will give better dispersion of the different lines. So that allows us to define something called the chromatic resolving power of any grating, where if I take two lines, lambda 1 and lambda 2, that are separated by some small amount, delta lambda, and lambda here is the average of the two lines, lambda 1 and lambda 2, then lambda divided by delta lambda minimum, where delta lambda minimum is the least resolvable wavelength difference. And this is the limit of resolution of your grating. Okay. So yeah, that's just defined here. If I have lambda 1 and lambda 2, then delta lambda is just simply the difference between them, and lambda will be just the average of the two wavelengths. So the Rayleigh resolution criterion, and this shows up again and again, is that the wavelengths have to be separated by at least half the instrumental broadening. So effectively what it's saying is, we know that coming out of the grating, if I were to plot as a function of theta, then lambda 1 will have some angle theta 1, and lambda 2 will have some spread in the angles given by delta theta that we just derived on the previous. Each of these is, delta separated by delta theta. Is the delta theta you can think of as, right, as I just explained to you, is sort of the angular instrumental broadening. And so you can see clearly here, when theta 1 and theta 2 are far apart compared to delta theta, if they're greater than that, then you can clearly resolve them. But as they get closer and closer spaced, the Rayleigh resolution criterion is that the wavelengths have to be separated by at least half the instrumental broadening. That means that the minimum delta theta minimum has to be at least the old delta theta, which is over here, which is this delta theta, the angular line width or instrumental broadening has to be at least delta theta divided by 2. So delta theta divided by 2, we derived it on the previous slide, is just this, lambda divided by Na cosine theta m. And from the angular dispersion, we know that this d equals d theta divided by d lambda. We can now use that to find what delta lambda minimum must be. So we just use that expression for d on the previous slide. Over here, m divided by d a cosine theta m allows us to tell if two lines are separated by an amount d lambda, then what is the spacing between them in the angle d theta. And that allows us to find delta theta minimum, which is delta lambda minimum times m divided by cosine theta. So now we can take the ratio of these two, and that immediately gives us the resolving power, R equals lambda divided by delta lambda minimum, right? So that is just immediately going to give us m times n. So basically I'm solving for lambda from this expression, and I'm solving for delta lambda in terms of this expression, and therefore I can find this value. So the resolving power is simply m times n. If I want to get rid of this m, which is the order, sometimes you just care about the order, so you don't need to get rid of it. But if you want to get rid of it, then m is simply obtained by substituting in the grating equation, n times a times sine theta m minus sine theta I divided by lambda. And that gives us the chromatic resolving power of a grating. So again, it's governed by the total grating width. N times a is the grating width, and of course goes inversely with the wavelength lambda. One other useful thing to know is how gratings are typically mounted in many different situations. When you mount a grating so that the incident beam is normal to the groove face, then the reflected beam, in the autocollimation condition, is that if gamma is exactly equal to theta I, then gamma is approximately theta I. If the incident beam is normal to the groove face, then gamma approximately theta I, and that's approximately minus theta m, the order, and that immediately gives us R, the autocollimation condition, which is when things become maximum, Na times sine theta I. If you go back one step, Na times sine theta m minus sine theta I. So what I'm saying is if I make theta m equal to minus theta I, or theta I equal to minus theta m, then I get this condition. So this litro autocollimation situation, or litro autocollimation condition, is very useful. As you can see here, the angle of the order is going to be exactly by just slightly altering it. You can see that there is a diffraction pattern that is projected here. This is sort of the three-dimensional view, and this is the side view. You can see that the beam, the original beam gets reflected back, and there is a spread in the other wavelengths. So you can choose which wavelength is fed back into the original cavity back here. Okay, and that into, for example, a laser cavity, for instance. And that allows us to build scanning lasers. We can only feed back one wavelength in the litro autocollimation grating condition. And the dispersion D in the autocollimation condition is also becomes independent of the slit width. So the slit or the separation between the slits, not the slit width, but the separation between the lines, this dispersion is just dependent on this incident angle theta I. So let's do one quick example. We wish to resolve the sodium D1 line doublet in the first order of a transmission grating. How many slits or grooves must the grating possess at a minimum? Well, to solve that, we just need that this R equals M times N, the total number of lines in the grating. And we just saw that and R, as we know, is defined as lambda divided by delta lambda minimum. And we just need to find lambda, which is just the average of these two wavelengths. So lambda 1 plus lambda 2 over 2 divided by 2. Which we can work out. I'll let you work that out. And similarly, delta lambda minimum in this case is just the separation between these two wavelengths, which is going to be let's see here, it's 0.597 nanometers, just the separation between them. And so that's it. So this is going to be approximately what, 589 point something, with some decimal, but it doesn't matter too much for us, for our purposes. So we want this this lambda over delta lambda minimum to be at least this much, right? So Mn has to be greater than or equal to this value, which we have obtained by finding lambda divided by delta lambda. So if I call that as some value x, which is just lambda divided by delta lambda, so n has to be greater than or equal to x divided by m, small m, which is just 1 in this example. If it had been 2, that just means that n would be half of the value you would need in the first order. So for the first order, you get a certain value, call it x in this situation, which is just the ratio of lambda to delta lambda. Then in the second order, it will be only half that many lines will be needed. Okay, so now if we used a grating with 10,000 lines per centimeter, how far apart in the first order spectrum will the lines be on a screen 1 meter away? For this, we need to find A. A is 10,000 lines. So that is 10,000, and 1 centimeter is 10 to the 10 to the minus 2 meters. So we are looking at 10 to the minus 6 meters, right? Because that's the spacing between them. So in 1 centimeter is 10 to the minus 2 meters, and then divide by 10,000, which is 10 to the 4. So that gives me 10 to the minus 6 meters for the spacing between the lines. And then we simply need to set A sine theta equals, we have already put the first order spectrum, so that's lambda 1. So I call that theta 1, A sine theta 2 equals lambda 2. So from this I get theta 1 and theta 2, right? You could also use the grating angular dispersion d theta over d lambda, but I'm just explicitly calculating the values for theta 1 and theta 2 directly from the formula for the grating equation, since I know the values. Or as I said, you can also use d theta over d lambda from the grating equation. Okay. Anyway, coming back to this, we can now find the position, call it y1, will be just approximately, right? So remember the grating, let's say the grating is set up over here, and there is a screen which is 1 meter away. Then if the angle is theta relative to the normal, right, then the position of this, if I call this distance L, and this is y, then y1 is approximately L tan theta, and L tan theta is approximately the same as L sine theta. And therefore, this is approximately L times lambda 1 divided by A. So that's the position of the first line. Similarly, the second line, y2, is approximately L times lambda 2 over A. And therefore, we can just calculate now y1 minus y2, just put those into the formula, and you get the solution for y1 and y2. So I'll let you fill in the numbers for this expression, and you can find out how far apart they are. I want to conclude the section on the diffraction grating by just talking about some common gratings that you can easily find lying around. So a good CD player, the CDs that you put into CDs or DVD players, if you look at them at any kind of glancing or even some acute angle of incidence, you immediately observe lots and lots of colors, which are the diffraction coming from all the different rulings of the on this CD player or DVD, CD disc or DVD disc. But also in nature, feathers. Here's an example from a bunch of feather. When you look at it through through this feather, you can observe diffraction patterns. Here's another example of peacock feather. All of these, due to the minute scales and the spacing between the lines inside the feather, give us a very good diffraction grating. Another beautiful example of that in nature is the butterfly's wing. If you look at high resolution at a butterfly's wing, you observe these lines, which are the cuticles of the butterfly's wing. And these scales or these cuticles form an excellent diffraction pattern. Here, for example, as you can see, it's specifically giving us a blue color, which is responsible for sort of the blue color of the butterfly's wing in transmission.